This is All Things Ansys, a podcast from the technical support staff at PADT. Episode 59, a discussion about what is new in Ansys MAPDL 2020 R1, and a look at the Ansys world. Welcome to our podcast, and what we hope you will find to be a bubble of normalcy in this surreal sea of disruption that's around us as we all deal with this coronavirus pandemic. My name is Eric Miller, and I'm one of the owners at PADT, longtime Ansys user and usual host for this podcast. And I am recording actually, from my upgraded home office. Went ahead, I'm going to be here a while. I'll talk a little bit about this, but we're pretty much working from home now. So I upgraded my desk chair, got some monitors set up a little bit more conveniently, and just kind of rearranged some things to give me a little bit more room because I'm going to be here, a lot. First and foremost, we hope that you are all very safe and that you're taking care of yourselves and your families. That's our number one priority. As I mentioned, PADT we're about 80% of our employees are working from home. We do have a manufacturing group for 3D printing, so they're coming in at different times to take care of the machines and get parts made, kind of keep that part of the business running, also fulfilling orders for 3D printing material, etc. But the vast majority of us are working from home, and I think the big thing that we found is that, we have the setup already because most of our engineers, especially our simulation engineers, work from home on a regular basis, whether that's at night or they do it during the day, when they need to be home with the family or whatever the reasons are. So, and we have more than a few employees who always work from home. They don't live near one of our offices, so they work from their home office. As soon as this looked like it was getting pretty bad, we went ahead and tested everything out, made sure we could make this happen, made lists of who needed what in order to be productive at home. And then pretty much on Friday, we moved everyone home. We're lucky here in Arizona. There hasn't been as much spread as other parts of the country. It is coming. It will come. So we were able to kind of get ahead of the curve and get everybody safe. That's true of almost all of our employees across the country. They live in places that haven't been as heavily impacted except for our employees in California. So our goal is to make sure everybody stays safe. That's the big thing. We're open for business. Ansys sales and support and training are going strong. If anything, they're more productive than they've been in the past. We have less meetings, so maybe they're getting more done. So if we do provide you with technical support, we'll probably be using email a little bit more than the phone, because we can't get our phones at home. So we're forwarding to cell phones. It's complicated, but just use email. It's much easier. And then we can call you back or use Teams. But by the way, I think we mentioned on the podcast that we made a major migration to Office 365 in January. It was a little painful. We had a lot of email issues transitioning, but it has worked beautifully since then. And I don't know what we would be doing if we had not made that transition. It sure makes our life a lot easier. So one of the things I'd like to ask is for you to take our poll about how you and your company are dealing with the coronavirus and how you're getting your Ansys simulation done. It's at www.padtinc.com/AnsysWFH. So that's ANSYS WFH, all one word, no spaces. PADTinc.com/AnsysWFH for work for home. It's a little distraction in your day and a way to see what everybody else is doing. And we're going to put it up there for 2 weeks. And at the end, we will go ahead and share the results to everybody. And at the end of the survey, we're going to ask you, if you want to participate in maybe a podcast. I'd like to do a podcast to just talk with folks about how they're working from home, kind of share their experience. And if you'd like to volunteer for that, just go ahead and click yes on that question and then give your email address, and we would love to have you on. So we'll share the results, though, from the survey on the episode that comes out right after April. I think it's April 3rd is when we close down the survey. So the 6th is when we'll send it out there. So today's interview, really a discussion, is a look at our favorite part of Ansys, the Ansys MAPDL solver, or like those of us who've been using the code for a long time call it, Ansys. This was the piece. If you're not aware, what we now call MAPDL was the original code that John Swanson wrote that grew into the company, the 1 billion dollar company that Ansys is today, and it started it all. But I get distracted. I like talking about that. Let's see what we found of interest in Ansys MAPDL 2020 R1. I want to welcome some of our engineers from PADT for a discussion about what is new in another portion of Ansys 2020 R1. I'm really struggling with the fact that it's 2020. We're going to talk about the mechanical APDL, elements, context, and solver updates. And with me today are Ted, Alex, and Joe. So Ted, why don't you introduce yourself?
My name is Ted Harris. I head up our simulation support group here at PADT, longtime Ansys user.
Alex?
Hi, I'm Alex Grishin. I've been here at PADT for 21 years. I'm in the engineering services department. I'm an analyst. I perform simulation services for PADT primarily, but I also help with tech support and training.
And Joe?
And I'm Joe Woodward, senior mechanical engineer and lead trainer, and I help out with tech support and sometimes services.
So we're kind of in a transition right now with the pandemic going on. Ted and I are officially working from home, and Joe and Alex are on their way. So next time we talk, I think we'll all be calling in from home. But for recording the podcast, it really doesn't matter because we usually do it from our desk these days anyway. So like I said in the intro, we're talking about release 2020 R1 and kind of the core of the program that all four of us used to live in all the time, and now is sometimes just the solver behind mechanical. And that's what used to be the original Ansys product that John Swanson wrote, which we now call mechanical APDL, and elements, context, and what's new in the solver. And let's just go ahead and start with the elements. Not a huge number of new or different things, and kind of esoteric. Anybody want to discuss? My favorite is the just because it's cool. I haven't had a chance to look at it. Is the cables, the cable 280? One of you said that you had played with that.
Yeah, that's me. This is Alex, and the cable 280s I can report do work very, very well. So one of the issues in the past with those was that you can have cable elements that go into tension and compression. Well, that is to say, they can be tension only, but go into a slack condition. And when they go into that slack condition, Ansys often fails. It depends on the refinement of those elements and how many iterations you have. And in fact, in the past, you would have it was not uncommon to have to crank up the maximum number of iterations to over 500 or even 1,000 to get those to solve, depending on the mesh refinement. Well, this element almost completely solves that problem. It now solves really fast and really well without having to do that, without having to play those kinds of games on setting the max iteration count. So yeah, I can report that those it's a really good improvement in that technology, cable modeling.
Mm-hmm. And some of the examples they show are, a cable going around a pulley, and then making strands, so like winding cables around each other. So it's pretty cool stuff. If you're dealing with cables, definitely something we used to just kind of avoid in the past, I think.
Yeah, and it's kind of a problem in a lot of industries. So, for example, I'm thinking in particular of like construction, people that build and design cranes and things like that have a lot of tension, long, thin members in tension that don't really supply a lot of stiffness, but definitely transmit load. And so in those situations, you need an element like this, especially when they have nonlinear deflection, which a lot of these guys do. When you have large nonlinear deflections, you need to be able to account for large changes in orientation with those members. So, for example, a follower load won't quite do it because that only allows you to sort of point to one point in space. So you have to use something like this. And so this is a really a great improvement for, let's say, that industry because it works really well. Good.
Excellent. Anybody else want to talk about any of the other cool things that are in the element library?
Well, it looks like they're adding to the capabilities for the inverse analysis.
Yeah.
With the solid 186, 187s, and now the solid 185s. I guess now they're supporting large deformation with incompressibility. So the example they show is an artery. They've scanned an artery, and you get the scan of what the deformed shape is because of the blood pressure. So you can go back in and put in the pressure on the internal faces, and then do the inverse analysis to find out what the artery would look like without the pressure. So
it's just pretty cool.
Usually we think of inverse analysis as kind of hot to cold turbo machinery type stuff. That was a new one that I hadn't thought of.
Yeah, it looks like it's calculating the diameters as well. So it's pretty complicated geometry when you get into these blood vessels and things, and so it's complicated math, and I think something that we would have had to have written a lot of scripts to do in the past, for sure.
Right. Well, and I think it accounts for the wall thickness change as it's stretching, and on the inverse analysis, as it's going back to non-stretched, it thickens up.
Good. The other thing is some work on the 2D thermal elements. So that's something that we don't use that too often. I think, Ted, you may have used those more than most of us, right?
Yeah, there are two new 2D thermal element types, plane 292 and 293. The difference is 292 is the linear 4-node option, and 293 adds the mid-side nodes. So what these do is they, I won't say replace, but they serve like the old plane 55 and plane 77, but bring those up to modern technology like the 180 series of structural element types. So they allow for more capability in material property definition. They support user programmable features, which the old ones don't.
That's a really good point. Yeah.
Just more capable, more modern, more capable.
It's interesting that there's still some elements out there that are getting updated that have been around for a while, but the older elements are still have a little bit more capability, and they're still kind of moving stuff over. There's a lot in there. It's a heck of a lot in there. And you mentioned the user materials. It looks like they've made some more enhancements to that as well in the 22X coupled field elements. Yeah,
usually in the past you weren't able to customize those, so now you can.
So people that aren't familiar with it, the coupled field analysis are more than just the displacement degree of freedoms, right? They can do other degrees of freedom, like voltage or thermal, or help me out here. What are the other ones? I'm drawing a blank. Electrostatic, right?
Yeah.
Right. In one solve, right? It's one matrix. It's not an iterative thing where I solve and converge, solve and converge. Yeah.
Turn on the degrees of freedom you want to use with the element options.
Yeah. So really cool capability. But if you're going to do some weird stuff, and maybe you're using another code whose name I'm not going to mention that has a much more open capability to write your own element equations, and I think this will help with some customers that may have one or two copies of that laying around, so they can do these sort of user routines for the multi-physics coupled elements. It's kind of nice. So Fortran is alive and well. Anything else in the world of elements before we move on to contact?
Well, one thing that I think I thought they'd released it already, but maybe they're adding to it, is just the ability to put pressure loads on solid and 2D or solid and shell elements without the need for the surface effect elements. So
right.
you can apply your pressures and things directly to the elements, to the solids.
Yeah. So if people are mechanical users, they're probably a lot of that happens under the hood, right? When you apply a pressure to something, it actually kind of paves the surface where you applied the pressure with what I used to call dummy elements. They're surface effect elements. They don't contribute to the stiffness matrix, right? They're just a place to put loads on and calculate what the load goes to the nodes that are shared on those surface elements. And this kind of gets away from having to do that. You can just apply them directly to the faces.
Yeah, anytime you add a non-normal pressure or a tapered load, tangential loads, things like that, you always had to have the surface effect elements.
Yeah. So it's a little bit simpler. I don't have to worry about that.
Right.
It's kind of nice.
Exactly.
Oh, good. Okay, let's move on to contact. So contact, of course, is very, very important in the world of simulation as we do more and more assemblies, and some improvements there. Again, adding more options and more capabilities. Even and they include this in contact. The bolt pretension is another thing that's changed. Does anybody have a chance to look in more detail at the new capabilities in bolt pretension?
Yeah, they're adding in the past, it was just constraint equations that would pull the bolt through each other. But if your joint rotated, then those constraint equations were written in the wrong directions.
Gotcha.
So your bolt's trying to pull sideways instead of axially.
Yeah, so that's been a limitation for a long, long time.
Right. Yep. Right.
Not valid in large deformation problems.
If you had any large deformation, my constraint equations were written in the original coordinate system, and then if I rotate in that coordinate system, they're no longer valid. Yeah.
Yep. Right.
Yeah. So how did they solve that?
Well, it looks like now it can put in an MPC 184 joint that will rewrite those internal equations for large deformation.
Because that element, that MPC 184 element, is large deflection and rotates. I gotcha.
Yep.
Right.
Mm-hmm.
Right. So that they've added that in to be able to account for large deformation. So I assume that's going to get put into mechanical pretty quickly once it's adopted here.
Good point. This is probably the first step, getting it to work in the MAPDL, the solver side, and then once it's working there, expose it in the interface. Yeah. So you could if you wanted to do it in mechanical, you could write an APDL script probably, right, to put these in there.
Right. Yeah. You just have to put in a snippet.
Mm-hmm. Yeah.
Cool.
So it might be as simple as just changing an element type.
Maybe actually, yeah. Something we'll have to play with when we get time. Which is not going to happen. I think we're so busy right now. In fact, I want to thank you guys for taking time to talk, because I know that I'm watching the number of support requests coming in. Even though a lot of our customers are moving home, the number of support requests is not going down. Mm-hmm. So. If anything, they're going up.
I've noticed a lot of them have turned to VPN connections and
yes, exactly.
Those types of things.
Ahmed, who handles a lot of our network related, IT related questions around licensing and such. I know that he's been a very busy person, as have all of you on that. There's a couple other things, like some more sophisticated. I don't know what you want to call them, algorithms for convergence. Like there's this, I like saying it, exponential pressure penetration relationship for contact elements. And it supposedly produces a smoother response. If you remember, the original contact elements were pretty straightforward, right? If you assigned a stiffness, basically a spring, and if one node penetrated the surface of the other side, it would just calculate the displacement and then times that times the spring stiffness and apply that as a restoring force. So this looks like a much more general or a subtle way of doing that, so it doesn't go back and forth because of the big change.
Yeah, it's intended to help with assemblies where contact has been difficult to converge previously, where maybe there's just slight forces causing contact to occur, and there's I don't know if bouncing around is the right term, but self-contacting problems where it just might be some difficulty with the traditional contact stiffness factor,
right?
Trying to get it to converge. So this technique should help us with difficult to converge contact problems like that.
Kind of as an alternative to the Lagrange method, maybe.
Yeah.
Or is that a different approach, probably?
Well, the Lagrange method is using basically pressure degrees of freedom, but by default, I think most of the time we're using the spring stiffness method first, and then the augmented Lagrange to fine tune it.
Okay. Cool. So it'll be interesting to see over time if this helps when we get some. I mean, we do get quite a few convergence questions for tech support, so it'll be nice to see if we have people turn this on and tweak these parameters so they can get faster convergence. Yeah. Good. Anything else anybody want to talk about? Just a lot of little changes in convergence and such.
Well, there's a new command, which is pretty useful, SF control, that allows you to give much more greater control over the direction of tractions on, on a surface. Yeah. So, that's pretty handy. You can do it in an element reference, element face reference, or by a local coordinate system reference if you want. It's pretty flexible. Whereas it's always been a little difficult to do that in the past. I've had to write scripts before to go element by element to define tractions, and it helps with that.
Good.
Oh yeah, that's part of applying pressures to the solid elements.
Okay.
Yep. I missed that when they added that control in there to account for the fact that they're not using the surface effect elements.
Yeah.
Cool.
Gotcha. Okay. Cool. That is good. I think if you're not a power user of APDL, a lot of what we're talking about may be kind of scratching your head. So that's a great example of where you should call your support provider, who's hopefully PADT, and we can help explain some of these things because it is getting down into the weeds inside the code.
Right. A lot of this, once it goes into mechanical, you probably won't even see it.
Right. There may be like a slider or something in mechanical, and what it's really doing behind the scene is saying, use this method or use that method or apply these parameters.
An example of that would be the use of MPCA 184s for bolt pretension now, right? I mean, that's the kind of thing that once it gets adopted in Workbench, it will be it'll transparent. You won't even know it. You won't even see it.
Yeah.
If you don't look
turn
at the file,
the nonlinear geometry on, it'll go and switch them to 184s, and you won't even know it.
Yeah, exactly. It just knows. So you're getting if you're just a mechanical user and don't get into the weeds, hopefully this gives you a little picture of what's going on under the hood. That there's a lot of cool stuff. Anything else on contact before we talk about speeding up the solvers?
No. Well, there's the fluid pressure penetration, which I mean that capability is not new. What is new is the ability for it to handle tangential load coming in instead of normal pressure, just normal pressure. So that expands the capability of having a seal with a pressure inside and trying to determine if that seal is going to hold or if it's going to come loose and the fluid is going to escape.
And I think as that fluid's escaping, that's where your tangential forces come in.
Right.
So that's why once the seal opens, then once it's flowing, it's pulling on the seal.
Drag across the seal.
Right.
Yeah, and this comes up a little bit. And I'm, of course, since I've had my leadership lobotomy, I like to call it. I don't get involved in doing these models anymore. But when I'm sitting in meetings talking with new prospective consulting customers, they often want to model these things as full CFD, and that's really not necessary, right? We've got these capabilities to approximate it with these kind of fluid penetration elements.
Yep.
Okay. let's move on to solvers. And if you've listened to these podcasts before or gone to our webinars, we always kind of talk about the same thing. It's faster. It uses less resources, and file sizes go down. So I don't know if anybody wants to give me details on any of those things, but that's pretty much it this time, right? Same.
Yeah. Yeah. What Eric said.
Good numbers. Yeah. Good numbers though, right? I mean,
right. Yeah, it's a little hard to show on the podcast, but they have quite a few charts on here on how much things have sped up and with their different models and different solution types.
And one of the reasons why I'm kind of excited about it is we're running more and more in the cloud. We just had our own hardware. I wasn't paying for the memory. I mean, I paid for it once, but I, used it over a very long period of time. Now I've got to spin up a box, right? How much RAM do I need for that box? Let's say I'm going to run on 256 cores. I'm looking at one particular case where they're seeing an almost, I think it's 35% drop in the amount of RAM needed at 2020 R1 versus 2019 R1. So over a year, it looks almost maybe even more than 35%, almost 40%. And that could be a big dollar difference in the amount of RAM that I'm paying for on that, either buying a machine or in our case where we're doing these large problems on the cloud, not having to pay for as much per CPU cycle for the RAM.
That's a really good point.
Yeah, that's like I said, with my leadership lobotomy, all I care about is how much does it cost.
One of the things I noticed in the release notes, now we have many, many people working from home, and I know a lot of them are able to VPN into their normal workstation or server or perhaps even cluster environment. But for those stuck on a laptop, there has been an enhancement to the sparse solver. So when running in out-of-core memory mode on Windows, the sparse solver is significantly faster for many simulations. So what that means is, ideally we want to solve in-core, but depending on how much RAM we've got and the size of the model we have, we may not be able to do that. So for many, many years, you could run out of core, but you paid a substantial penalty in solution time. So it's really good to see, it's very timely to see that they have enhanced it to be significantly faster, at least for some simulations, if not many.
That's a really good point. People may not have access to the compute horsepower they had in the past because they're working on their laptop. And the solution used to be, right, it's okay, well, I'm running out of core, I'm just going to set it up in the corner and let it heat up my room for 2 days. That's a nice improvement. Cool. The other thing was just the speed up. I don't know that there's anything significant other than they got in there and tweaked some stuff. And getting some big speed ups depends on the problem and the number of cores, et cetera, but some nice improvements. Don't know if there's anything worth it. There's not a lot of details of what they tweaked, but just improved sparse solver performance, right?
Right. Yeah. They don't really give details on what they're doing, but they they don't want to give away the secrets, just the outcome.
I think in this case, it's I/O changes on Windows. So using some of the enhanced capabilities within Microsoft is doing things, I guess, every once in a while. So calling those subroutines to do I/O may be making a difference there. So definitely try it out. Even one of the examples they give is a 9 million degree of freedom sparse solve out of core memory node, and by tweaking the I/O functions using these Windows I/O functions, it looks like on 2 cores. It's almost twice as fast. 1.8 times faster, 1.9 times faster. And then if you go to 12 cores, you're not getting as big of a benefit, but you're still speeding up 1.35 times. So it's pretty cool. More value for you. People are always asking, why am I paying for text? That's one of the things you're paying for.
Yeah, but a lot of development going in a lot of areas.
They're not leaving it static. Anybody want to talk about the smaller? I think one of you, when we were talking beforehand, said that this was kind of the biggest thing in this section is the fact that the files are smaller. The database files are smaller.
Oh, I think so. I think that's big. It's big.
It's kind of buried.
They would lead with that, but no. Yeah, and for both RST and DB files, right? If anyone is familiar with in the past, trying to compress those files, well, they just wouldn't compress any further if you used the traditional, Windows-based zip or 7-zip or something like that. Whatever compression algorithms they use just wouldn't compress them any further, right? So I think the line that was always given was, well, they're already compressed, right? Okay, well, apparently there's a new algorithm they're using. What is it called? Sparsification.
Yeah.
Sparsify.
Right. So they're using something new to compress these guys to, again, a factor of 35 to 40%.
Yeah. In fact, it looks like
that's huge.
Looks like it's from 20 to 90, depending on 90%, depending on the model that they're looking at.
That's true. Yeah, that's right.
Some of the models are significant.
Quite a bit spread.
Yeah. Average is 35. So again, like Ted was mentioning, with a lot of us moving to work from home, you may be, say, solving on a desktop system that's sitting alone in your corporate headquarters, right? In the cubicle all by itself. And you want to pre and post process or post process on your laptop back at home. So, bringing that file back and forth, or maybe you're solving at home and you want to store the files when you're done back on your corporate server. Bandwidth is, we don't want to slow down streaming because that's what we're doing when we're not working now. So compress these files. So what we're talking about is not changing what's being written to the file. It's just a much better compression algorithm. And you do it. It's on by default, I believe. Is that correct? Yeah.
I believe so. Yeah.
Yep. There's a command called fcomp that allows you to either turn it off or change to a different format or different compression level, right?
Well, I'm curious so you would want to turn it off if you've got. Why would you want to turn it off? Let's say
it takes longer. I think that's the only reason.
Oh, okay.
The only reason is it does take a little bit longer now. And in fact, there's a level right on the sparse. So there's two arguments to the fcomp command, right? There's a level argument. That's the sparse argument, and if it's the default, you use the sparsification scheme to compress the file, and that takes a certain amount of time. But if you switch it to level 0, then nothing happens, and it's the same thing as it always was. But you can also use a number from 1 to 5. And what it'll do is it'll create a zibli-based compression that occurs at level number n from 1 to 5. And so, it's like choose your level of compression sort of thing. The highest level will take the longest, et cetera, et cetera. So I think one of those options will actually compress it even farther than the default.
Wow. Okay. So play with that. I mean, that's probably one of those things where if you're running locally and you got plenty of disk space, go for the performance. Save the database files as fast as you can. But if you are moving files around, or IT's still getting mad at you for the amount of disk space you're using, then try this out, and it can make a big difference. I know we've been in crunch times where it's like, I'm out of disk space, and I got to get this model done, and you're deleting stuff you probably don't want to be deleting. So this could, over time, could free up a lot of space.
Oh yeah, it's huge.
Okay. Anything else on that before we talk about this? For some reason, it makes me think of some British movie, NLAD. So who wants to explain what NLAD is? Because I always get tongue-tied when I say it, and why we care.
Okay, I'll take a stab at it. So it stands for nonlinear adaptive meshing, and you use it in situations where you have, the iconic situation would be if you have some very soft materials with an exotic nonlinear behavior, like let's say hyperelasticity or something like that.
Okay.
Where you have two pieces of rubber that are folding upon one another. Well, that wreaks havoc on the nodes and elements underneath the mesh. And so what nonlinear adaptive meshing does is it goes through and it starts remeshing as it solves in order to alleviate some of those problems. Like if an element's starting to get too slender or skewed or compressed, it will remesh that element. So, and you can do so based on different criteria. Like there's an energy criteria. There's just a there's a quality criterion that you can use to remesh. And so there have been some updates in 2020 to that. So in the past, in fact, they've been making steady improvements to this with almost every release, or at least every other release, major release. And so that one of the big deals at 2020 R1 is to allow the use of this technique without having nonlinear geometry effects on. So you can have it. You can do it, for example, to just a model that has, let's say, a bilinear isotropic hardening model, and it's nice because it will, even though it may not save you a lot of time or headache in terms of convergence and all that. What it will do is it will produce a better result up front one time. It'll give you a good, solid result without having to iteratively refine your mesh.
Right.
So that would be
basically refining the mesh for you.
Yeah.
Right.
While you're solving.
Yeah.
Right. During the solve, right? Is this available in mechanical yet?
Well, nonlinear adaptive region is not sure about this
particular
latest capability.
Okay.
But
so you might have to snippet it in. Yeah.
Snippet it in if you have to.
So it's kind of like we were talking about with contact. If your model's just kind of blowing up on you for various reasons, and in this case, it's that your elements are getting funky and distorted and becoming unstable. This is definitely something to take a look at. Yeah.
Yep.
It's cool. And in some ways, I think we're making it too easy. People need to suffer more.
Well, and it's a very sophisticated technology, I guess we should say, right? Because
under the hood,
a user might naively think, well, duh, of course you want to do this when you have convergence problems. But the problem is that anytime you talk about refining a mesh or changing a mesh in any way, you're talking about changing the stiffness matrix,
right?
And you have to be really, really careful if you're going to do that during a solve, right? And so that's why some really, really sophisticated algorithms are going on underneath the hood to make that work in a robust way. And that's one reason too, I think, why the improvements have been incremental.
Right. It's not trivial.
And I think another point is you typically don't want to do this on the entire mesh.
Yeah.
If you have any kind of large model, you may find that it will, if you didn't have some controls on it, it can easily make a mesh that's so big you can't solve it. So you need a way to control it where it's going to occur. And because of that, the program needs to be able to map the state of the solution when it stops to remesh whatever portion you want it to do, and you have control over that before it continues the solve with that localized finer mesh. So that's another big part of the sophistication of it as well.
That's a really important point. What it's not doing is saying, oh, I need more elements here, stop, remesh, and go back to the beginning and start again. It's taking the strain field prior to the remesh and then applying it to the new mesh, converging on that, and then moving forward.
Yep.
It's just pretty sophisticated. Yeah, I love it. There's a few other little things that are exciting. We'll kind of looking at, we've got on the mechanical side, We've got the ability to put in probes for springs, beams, and joints, right? So these are simplified elements that are exposed in mechanical that are under the hood, or these kind of crazy multi-function Swiss Army knife elements in APDL, mechanical APDL. But and you had to write scripts to access the results from those. So now you can put these probes in and get how they behave. I thought that was kind of cool. Anybody else kind of randomly want to talk about?
I think I'm good.
I think, we're just talking about some of the things that are heavy hitters as far as we see, but we're certainly not talking about all of the enhancements. So the release notes are a good source of additional information.
Always, because there you may go, I was really hoping for this feature that I've been asking for a while, or I think would be useful, and we just didn't cover it. So always check the release notes or contact your support provider to find out more about this stuff. And so I think we'll just go ahead and finish it here with the note that we talked for a long time and we just scratched the surface. So read the release notes. We're headed into the weekend after 2 extremely crazy, insane weeks. So I want to thank you guys and the rest of the support team for dealing with everything that's going on in the world and keeping our customers productive. So thank you very much for that.
My pleasure.
You're welcome.
Next time.
All right. We'll see you guys next time in 2 weeks. Thanks.
Bye-bye.
So we hope you found that useful. There's some good stuff in there. Much of it is under the hood. Most users won't even see it. But it really is more capability, more robustness, and more speed so we can be more productive. So it's time for a commercial. I'll just read this a little bit right here. Please consider PADT as your Ansys supplier if you are in the southwestern U.S. and simulation consulting and customization supplier. We are also just as good at additive manufacturing and product development, so give us a try. We love what we do, and our customers tell us we are good at it. And I'll add that in these times, which are very difficult, you may be facing some challenges you've never expected. They may be hardware, they may be software, they may be logistics. You may be being asked to be doing simulation you weren't doing before because, who knows? So PADT is here to help. Just reach out and let's figure it out together. If we don't know how to do it, we may just know somebody that does. So communication is going to be key over the next months. News-wise, we always start with the Ansys stock, and I thought about skipping it, but to be honest, it's not as bad as it could be. It's at 213.11. That's down from a high of $299.06. Oh, by the way, I'm recording this on Sunday morning, which is let me look up the date, the 22nd. March 22nd, Sunday morning. So these are the numbers from Friday, which is going to be, can I do that math in my head? It's going to be the 20th, when the market closed on the 20th of March. So it's at 213, like I said, down from that high of 299 on February 19th. That's a 25% drop. The S&P 500 is down 32% for that same period, February 19th through last Friday. So yeah, Ansys is doing better. Nobody's doing well, but Ansys is doing better. If we look at year to date, Ansys is down 16.7%, and the S&P, now remember Ansys was at an all-time peak right before the market crashed. So it's gone down 16.7 since January 1, and S&P is down 28.5%. So that's a big improvement with Ansys for year to date. So part of me wants to hide and not come back for another 6 months and see what happened, but we'll keep an update and comparing it maybe to some of the other companies in the sector and see how Ansys is doing. We've got no new news from Ansys. Nothing. They haven't bought anybody. I think they're hunkered down, and PADT is hunkered down, so I don't have anything new to share as well. My 3 article picks for the Ansys blog, and you can get to the Ansys blog by just searching on Ansys blog or going to the Ansys website, going to About Ansys, and finding the blog there. My first pick was an interesting article that shows how regulations can impact design, and that in order to meet those design impacts, you got to use simulation. It's called "What is Right to Repair and How Will It Affect Product Design?" In the EU, they passed some regulations that basically said people should be able to repair their own appliances using common tools, no special tools required, and that companies have to keep the spare parts around for 10 years. And this means you got to design things to be repairable by non-experts, and simulation is a great way to do that. You probably want to make your products more robust as well, because it's going to cost you otherwise. So it's kind of cool how the flow happened. The second pick was the Sherlock team talking about keeping electronics cool. They always have some great insight, and it's becoming more and more of a problem as time goes by. It's called Thermal Management Systems: How Hot is Too Hot. So I found that useful. And then kind of on the cool factor side is an article called The Remarkable HMIs of Futuristic Cockpit Designs. Now, I did have to look up what an HMI was. It's the human-machine interface. So these are kind of what they call a glass cockpit, or a cockpit that's all LCD screens and all sorts of fancy, cool stuff. So if you want to know what airplanes are going to look like in 10 to 15 years, or maybe sooner, check out that article on the Ansys blog. We don't have any new articles for the PADT blog, although we do have one that'll come out next week, if I can get to that, amongst all the other stuff we're trying to do to keep things running forward. I'll get that hopefully out in the middle of next week. We do have an upcoming webinar to talk about what we talked about in the podcast today: Elements, Context, and Solver Updates in Ansys 2020 R1. And that's going to be Wednesday, March 25th. As usual, you can go to Bright Talk and search for PADT or Ansys and find it, or you can go to our website and go to the events page and register from there. We don't have any events coming up. In fact, everything's been canceled. So we do have that webinar, and we're putting together some 3D printing webinars. We tend to do 3D printing events more face-to-face. It's a kind of a technology you got to see, but we can't do that. So we're going to be doing a lot more online stuff. So do check that out on our events page. So that's it for today. You will find in our survey how annoying is your pet, or is a pet a distraction for you? My dog is scratching at the door, so I'm going to sign off. I want to thank you. Don't forget to subscribe at www.padtinc.com/opt-in. Please do take our survey that I mentioned at www.padtinc.com/AnsysWFH. Spread the word about the podcast. Don't hesitate to reach out. And of course, please stay home, stay healthy, and use that social distancing, right? You're a simulation engineer. You're probably not the most outgoing person in the world. Now's your time to shine. So let's try and make the world a better place through simulation from home for a while. Thanks. Thank you for joining us for the All Things Ansys podcast, episode 59. As a reminder, this podcast is not affiliated in any way with Ansys Inc., and the opinions expressed are those of the people on the show only and not of their current or former employers. For more information, visit www.padtinc.com/blog, and please share your thoughts and questions through an email to podcast@padtinc.com. See you next time.